Okay, so let's get started. I can't believe we're already lecture 9 in this series. I hope people are able to follow along. Today, we're going to start out by reviewing something that in previous semesters I've done at the very beginning of the class, which we covered a little bit, but it occurred to me listening to student presentations last week that it might be useful to review a few of these ideas. I think people are getting them, but they're important enough that we'll review them. And that may take a substantial chunk of the class, depending on how it goes. And then I wanted to give a very quick example of how you could do approximation of delay equations, because there was someone who was interested in replicating a model with delays in it. Antimony doesn't allow you to do delay equations in a formal way, but there's some quick and dirty ways that you could approximate them, and I wanted to cover that. And then I'd like to have time for the people who didn't get to present last week to present their work. And then we'll continue, I hope, with the immune response model that we had done 2 weeks ago. So I guess to begin with, let's see, who did not present last week? We had, did anyone who's on the call now not present last week? I know Jeffrey did, Collie did. Or is everyone who's here today is one of the people who presented last week, I think. Is there anyone who didn't present last week? Okay. So we'll have to do that. We'll have to kick that one to next week, I guess. Or if people join in later, we'll do that. So what I wanted to talk about today was a little bit about how to use the 3 formal specification languages that we have for describing models. And those formal specification model languages that we have are diagrams. Those would be things like the picture on the right. One of them is more graphical, one of them was more text-based, but these are the same equivalent diagrams. Representing here the infection of susceptible cells becoming early infected cells, becoming late infected cells. Those late infected cells produce virus. The virus decays, and the late infected cells also die. That's written in a more formal way below. And what we see is a set of arrows that denote transformation. And each of those arrows is labeled by a rate. And this set of diagrams here is precisely equivalent to an ODE model or to an antimony model. There isn't any ambiguity in that specification. The diagram at the top doesn't have the rates included, and therefore it needs additional information to be turned into an instantiable model. And one of the things that you're going to have to do repeatedly, especially in projects, is translate back and forth between the various kinds of notation, whether it's going from a diagram like the one at the top or a diagram like the one below it to ODEs, from ODEs to an arrow diagram, from either an arrow diagram or ODEs to antimony, or sometimes from antimony back to ODEs or arrow diagrams. And so what I wanted to do today to begin with was to do a series of simple exercises that will give us some practice in doing that transformation. And I know this is something that takes some practice. It's mechanical in the sense that there is a simple set of steps that you need to go through to do it. But like anything, until you've done it enough times, it's a little bit alien and it's easy to make mistakes. Once you've done it enough, I hope you'll find it something that you can do in your sleep. So the first thing that I want to come back to is just arrows. These are slides that I would have, if I were teaching the course around chemical reactions, and you'll see some of these slides are more oriented towards chemical reactions than the things we've been doing here. Around chemical reactions, this would have been the first or the second lecture. And so the first thing we want to think about is suppose that we have a chemical reaction or some other reaction, A plus B goes to C. And we want to know how the amount of C depends on the amounts of A and B as they change in time. And we covered this before, and typically we'll use the italic form of the letter to represent the amount of A, B, and C. And we'll write over the arrow a rate or a velocity, which is the speed at which A and B combine to make C. And this says chemistry. I meant to take the word chemistry out because this comes from a slide on chemical reactions. But if we have some set of experimental conditions, chemistry or not, then the rate of transformation from A and B to make C ought to depend primarily on the amount of A and B. And so the velocity, VF, should be a function of A and B, the amount of A and B, or the concentration of A and B. Now, we've talked a little bit about when this kind of approximation, which will generate ODEs, makes sense. One is that the amounts or concentrations of each of these species, A, B, and C, are large enough that we don't have to think about it in discrete individuals. And a couple of weeks ago, we did an example where we didn't have that apply. And infection, when you're getting started, is a classic example of that. If you have one infected individual, that is very different from having 10% of your population infected. And we also assume that the rate of change is over a large enough population that we can assume that it's deterministic. And again, that's something we relaxed in our discussion when we did Gillespie algorithm for infection. And if anybody was able to hear the talk that Alessandro Vespignani gave last week, then he's doing an even bigger relaxation of that kind of approximation. We're also assuming that there are no spatial effects, that every individual A is equivalent to every other one. Every B is equivalent to every other B. C is equivalent to every other C. That's something that in my research we typically don't assume. And it's clearly, again, not going to be true in large populations. If there's somebody who's infected in New York, the probability that you're infected by that person when you're in Wyoming is very low. So there clearly are spatial effects. And so if we have those assumptions, then we can write a set of ordinary differential equations we've done many times now. And I just want to remind you, if you have the arrow diagram, A plus B goes to C at a rate VF of A and B, that generates 3 ordinary differential equations, one for each species, A, B, and C. A and B are called substrates. They're on the left-hand side of the arrow. C is called a product. It's on the right-hand side of the arrow. And that means there's a minus sign in front of the rate for A and B, and a plus sign in front of the rate for C. So this one arrow diagram generates 3 ODEs. dA dt is equal to minus VF of A and B. dB by dt equals minus VF of A and B. dC by dt is VF of A and B. Now in chemistry, you can have what are called reversible reactions, where you'd have a back arrow going from C back to A and B, and that would be labeled separately with a rate law for the reverse. In this class, we'll pretty much always, if there is a back reaction of that kind, have a separate arrow separately labeled. We won't use a double arrow notation. Chemists like that. Again, there are a variety of different kinds of arrows and notations for what's going on. Essentially, an arrow connects nodes. The nodes have a state, which is a concentration. The links or arrows represent transformations between substrates and products. And in principle, they can take an arbitrary number of substrates, here 2, and give us an arbitrary number of products, here 3. And if we're doing chemistry, we have what's called stoichiometry, which is, for example, you could have hydrogen and oxygen combined to make water. H2O, you need 2 hydrogen for each oxygen. Oxygen comes in units of 2. And so your equation would be 2 H2 plus O2 goes to 2 H2O. That would be the chemical reaction for water. Again, in the particular approximations we're using in epidemiology and in viral replication, we're typically not going to have complicated stoichiometry, but it came up when we thought about what would happen if we used up virus when it was infecting a cell, because we didn't necessarily need 1 unit of virus to infect 1 cell. We might have needed a smaller amount. That would be a stoichiometric number. There's an old convention for chemistry that you sometimes use multi-tailed arrows or multi-headed arrows to give the number of molecules. That gets pretty awkward if you've got lots of molecules. What's more common is to use a number in front of the species name, like that. Here you see these double-headed arrows that chemists like to show bidirectional reactions. There's another notational feature that we're going to run into, and we'll run into it today. This comes about mainly when you have signaling networks or gene regulatory networks, but it also occurs in the cases that we're dealing with, which is that if we have a species S1 and a species S2 and an arrow between them, that means S1 is being destroyed and S2 is being created. And in this case, the arrow is linking a species name to another species name. We will also see arrows that point to other arrows. And in this case, A is pointing to the arrow between S1 and S2. And there's some inconsistency in notation, but in general, these lollipop arrows with the circle at the end mean that the more A there is, the faster S1 is converted to S2, in which case A is called an activator. And if there is a T-shaped end to the arrow, the more R there is, the slower S1 is converted to S2. And these are called regulatory interactions. And those are extremely important in the models that we're building and in almost any biological network. The key difference between the arrow with a pointed end and the arrow with a lollipop or a T end is that S1 is used up to create S2. A is not used up in this reaction. It's just modulating it. And that's the key difference between a regulatory and a transformational arrow. And it's important when you're writing equations or interpreting equations to remember that difference. And one of the places that it's easiest to get confused or to make a mistake in interpretation is to turn a transformational arrow into a regulatory arrow or vice versa. So the example I gave here was S1 is going to S2, and it's activated by A. That means the more A I have, the faster I produce S2. Here, R inhibits the transformation of S1 to S2. So the more R I get, the slower or the less S2 I get. There's a bit of an annoyance in the biological literature, which is very often the source term S1 is not written. And so you'll see a shorthand for this correct notation, which is A has a lollipop arrow pointing at S2. And in principle, a regulatory arrow should only point at another arrow, not at a species. And so if I see A promotes S2, the output of that should be the same as what I had on the left. If I say R inhibits S2, the output of that should be the same as what I see on the left. But there are a lot of things that aren't being written down when you write an arrow diagram like that. And so you actually have to do some mental reconstruction when you see that. So if I see the diagram A promotes S2 like that, I have to interpret that as a chemical reaction, which is nothing is producing S2, and A is regulating the arrow, activating the arrow that goes from nothing to S2. And that would mean that, in fact, in standard notation, nothing goes to S2 with a rate, V1, that depends on A. That would be essentially equivalent to the second diagram that we wrote first. The same thing if I say R inhibits S2, I interpret that as nothing is going to S2, and the rate of production of S2 from nothing is inhibited by R. And so again, that would formally be nothing goes to S2 at a rate V1 of R. And we've already done this in a number of cases. When we had births, we had individuals that were being created, susceptible individuals that were being created from nowhere. And so anytime we have individuals coming into a population from outside, we have nothing goes to something in a transformational arrow, and that with some rate. So we've actually already done this without talking about it in detail. Okay, so what I'd like to do now is come back to the arrow diagram that we worked on before, and I'd like to do a series of very simple exercises using things that we've already played with to build a little bit of familiarity with how to translate back and forth. And for people who've done this before, that's great. Looking at the presentations last week, I think people were beginning to get the idea, but we're still having a little bit of trouble sometimes when you were reading an article, trying to think about how to interpret it. And so the reason I want to do these exercises is to make sure that if you pick up an article, it's not in the textbook, that you know how to handle these transformations. So we're going to take our example for our viral replication model. Our susceptible cells become infected with virus. This actually should be a lollipop because in this case, I'm not using up the virus. So my notation is bad, but at least the arrow is pointing to another arrow. I1, T becomes I1, I1 becomes I2, I2 produces virus, so that's a correct transformational arrow, although I2 is not actually used up in that. So perhaps you should think of that as a regulatory arrow too. So maybe there should be nothing goes to V, and the arrow should be pointing at that arrow. And I2 goes to D. So this top picture is a little bit ambiguous. The bottom picture is not ambiguous. The bottom picture is our susceptible cells go to I1 at a rate beta VT. Our I1 cells go to I2 at a rate KI1. Our I2 cells die at a rate D times I2. And then you'll notice that the virus here, and these are dashed lines here, which indicates regulation in some notation. The dashed lines here have nothing goes to V, and V goes to nothing. V goes to nothing at a rate C times V. Nothing goes to V at a rate P times I2. That is, it depends on the value of I2. So it's a regulatory interaction. So the first thing I'd like people to do, and this is something you do with a piece of paper. So if we can get a piece of paper and a pencil out, that would be great. Is we're going to take this diagram, the second one, which is unambiguous, and we're going to write ODEs from it. And I'll do the first one with you. And then the assignment, which will just, I hope, take a few minutes, will be to write the other ODEs. So we look at the first arrow diagram. We have T goes to I1. T is a substrate, which means the rate of change of T will be minus whatever is written on top of the arrow. And it's going to produce a product, I1, at a rate BVT. So the equation for dt will be dt by dt is equal to minus, because t is on the left-hand side, beta vt. You're going to have to write an ODE for each of the species, and I actually have left out D here, so there are actually going to be 5 ODEs. There'll be 1 for T, 1 for I1, 1 for I2, 1 for D, and 1 for V. And so what I'd like everyone to do is look at this diagram here and write down the other 4 ODEs. The one for I1, the one for I2, the one for D, and the one for V. Okay. Remember that if you have a single arrow like this that connects T and I1, that will have effects on 2 rate equations. It will have an effect on the rate equation for T and an effect on the rate equation for I1. In principle, if a species showed up multiple times, suppose I had 10 arrows all pointing to I1 or away from I1, then I would have multiple terms in my equation for I1. In this case, as a hint, there's 1 arrow pointing at I1 here. There's 1 arrow pointing away from I1 here. That tells me my rate equation for I1 will have 2 terms. Is that clear? So I'd like everybody now to take just a few minutes and write down the ODEs that correspond to dt by dt, di1 by dt, I2, and so on, based on this diagram. Okay. And as usual, I'll use the poll, and the poll will say, don't fill in the poll result until you're done. And so that way I'll know when everybody's ready to go on to the next step. And if anybody has a question about how to do this, anything that's confused, please put it in the chat or unmute and ask. Because the things that we're going to do today are essential skill sets for all the things we're going to do in the class. And I'll point out that when you have complex stoichiometry, like suppose I had T plus 1/100th of V goes to I1, then writing the rate laws is a little bit more complicated because you have to make sure everything is consistent when you add things up. But in these cases where you have one element of each thing on either end, then it's a little easier to do. Does anybody need more time now to finish up? Okay, so in this case, I wrote the first term, T goes to I1. We did that one, T dt by dt is equal to minus beta Vt. Because I1 is on the right, that also gives us a term, di1 dt equals plus beta Vt. I1 also shows up in that second arrow diagram. I1 goes to I2 at a rate ki1. That gives us the term di1 dt equals minus ki1. And so I have to add those two together. And that means di1 dt is minus equals to beta Vt minus ki1. And I have this hangover di2 dt equals ki1. I look at the third term, I1 goes to I2. That gives me, I've got I1 here. I've got the hangover term is di2 dt equals ki1. The last term, di2 dt gives me a di2. That gives me minus di2 for I2. So di2 dt is ki1 minus di2. dd by dt is equal to little di2. There's only one arrow pointing to d. V is independent. And so when I do V, I have nothing goes to V at rate PI2. So that gives me a plus. And outside, going out, minus CV. So So dV dt is equal to pi2 minus CV. Did everybody get that? Does anybody have an issue with that? Again, this is a relatively simple case. These can get more complex, and it's easy when you have a lot of terms to lose one. But the basic concept, I hope, is clear. Okay. One thing that you should be aware of, and we're going to run into it in the homework, is that just the way the arrow diagrams can be used, there are different conventions for the arrows. Dashed line for regulation versus lollipop, for example. There also are some inconsistencies in notation on how the rate laws are represented. So when I draw an arrow diagram, I will always put whatever the full rate law is on top of the arrow. So T goes to I1 at a rate beta VT. In a lot of chemistry literature and in some biological literature, the assumption is that whatever the substrate is multiplies the rate. That is, you write the rate constant rather than the rate law. And so this equation here will be written T goes to I1 with beta V on top of it with no T. And the question is, how would you know? You just see the diagram. Well, you have to think about what's meaningful. So for example, suppose I had this form here for the decay of my virus. It would turn V goes to nothing at rate C times V into V goes to nothing at rate C. I know I can't have a negative amount of virus. And so if the amount of virus decreased at a constant rate, when the amount of virus went to 0, it would keep going down and it would become negative. And so if I ever see a decay term which just has a constant on it and isn't multiplied by V, then I know they're following the convention that they don't multiply any of the terms by the source amounts. And so you have to multiply all of the terms by the source amount. To some extent, you can see that already in the equation here. T goes to I1 at rate beta V. If you ran out of T, if T were 0, this rate doesn't go to 0. And since we know the amounts of our species can't go negative, that doesn't make any sense. And so you have to be aware of that. The one place that that doesn't work, and that's why I prefer always to write the full rate law, is if I have nothing goes to V here, there wasn't anything to multiply by, and so that one rate law won't change. And so you'll see this diagram here, T goes to I1 rate beta VT is written T goes to I1 rate beta V, and so on. But this arrow, nothing goes to V at rate PI2, will still be nothing goes to V at rate PI2. And so specifically for any arrow that starts at a species, you need to multiply by the species amount. But for an arrow that starts at nothing, you don't multiply. Or you could say you multiply by nothing, but not 0 by nothing. Okay, and so that's something that you have to be aware of. I can't help the fact that the notation in the literature is inconsistent. And I'm giving you a heads up that in the homework problem, they use this notation. And so when you do the interpretation of that problem, you have to remember that. Okay. So we've done the case where we went from the arrows to the ODEs, and that was pretty straightforward. And now let's think about going the other way. Somebody gives us a set of ODs. We want to write the arrow diagram. That sounds easy. And in the cases I'm going to show you, it is easy. But in general, while the arrow diagram has a unique set of ODEs associated with it, ODEs do not have unique arrow diagrams. There are many arrow diagrams that can give the same ODEs, whereas any individual arrow diagram can only give one set of ODEs. And it's because of that lack of invertibility of the ODEs that people like me and Herbert strongly prefer the arrow diagram notation to the ODE notation. And as I mentioned, I think before in some previous years, I've given examples where we've taken papers, some very famous papers by some very famous mathematical biologists, given the ODEs and say, what is the set of chemical reactions that gave rise to these ODEs? And you can't figure it out. The ODEs are right. They do describe what's happening. But unless somebody gave you the diagram, there's no way you could infer what the underlying biochemistry was. Whereas given the arrows, you can always infer the ODEs. However, in simple cases, you can go backwards. And for some set of ODEs, you can always write down some arrow diagram that gives those ODEs. The only problem is it may not be unique. But there are some tricks. So one of the things that you'll notice is what's called balance equations. Let me see if I can use my new pen, my new drawing pen here. Okay, so you'll notice that the arrow T goes to I1 produced a term minus, T goes to I1 produced a term minus beta VT. And that corresponds to a term beta VT here. I have a term KI1 here minus and KI1 here plus. I have a term minus DI2 here plus DI2 here. If I added all of these up, this term plus this term plus this term plus this term, added them all up, I'd get 0. All of the terms would cancel. That's typical of when you have chemical reactions or transformations. You'll notice in this V1, I don't have any help. I don't have anything that balances either this or this. When I see a balanced term like this, minus something plus something in a pair, I will almost always interpret that as there being an arrow that connects T to I1, with the minus term being on the source side and the plus term being on the product side. In this case, I have T goes to I1 because of this balanced term. I have I1 goes to I2 because of this balanced term. I have I2 goes to D because of this balanced term. Okay. So when I look at a set of equations that I haven't seen before, like these ones over here, the first thing that I'm going to do if I want to write arrows is look to see if there's a balance. Minus K1A plus K1A. That means I have A goes to B, and the rate is K1A, at rate K1A. So your first assignment would be look at that 3 ODEs and write the arrow diagram for it. The second one is I've given you a slightly different set of ODEs. dA by dt is equal to minus K1AB. dB by dt equals minus K1AB, dC by dt equals K1AB, dd by dt equals K1AB. I want you to write an arrow diagram for that. Okay, so that's our next little exercise. Again, this is purely a pencil and paper exercise. And if there's something that's not clear or you need advice or help with this, feel free to ask. That's no problem. And I want to emphasize that it's not that there's necessarily a right or wrong notation. Sometimes ODs are more convenient, sometimes arrows are more convenient. But since we're going to run into all of these in the textbooks and the literature, we need to know how to interpret them. And I maybe should say that when I do this for complicated diagrams, I always have to recheck it and recheck it because it's very easy to leave terms out. So it's not something that's automatic. And the homework will give you lots of practice in doing this. But I want to make sure that everybody can work through some simple examples in class so that the homework isn't frustrating. just checking with people to see how you're doing with this. If anybody needs help, please ask. If you're done, let me know. So one person didn't answer. Are you stuck, or is it something you want to work on? Okay. So if I took the ODs that we started with here, we see we have the balance terms minus Ka, Ka. That means we get an arrow from A to B. We have the balance terms K2B, K2B minus plus. That means we get an arrow from B to C. The rate here would be K1A. The rate here would be K2B. So those are the equations. And I can compress those if I have the same thing on two arrows by combining them and writing that in one line like that. Should be like the second line here. For the second one, I notice that I have A with a minus sign, B with a minus sign, C with a plus sign, and D with a plus sign, and I have the same rate for all of them. When I see the same rate for everything, that usually means there's a single arrow. And so this has the form of A plus B goes to C plus D at a rate K1AB. The next thing we want to do is learn how to turn these things into antimony. The easiest thing is actually turning arrow diagrams into antimony. We've done that a lot. When people were trying to convert ODEs into antimony in their projects, some people were having finding that a little bit confusing. And so I want to go over that a little bit more. One thing to do is to take your ODs and turn it into arrow diagrams on a piece of paper before you code it into antimony. I mean, that's not a bad idea. The other thing is that if you really, really want ODEs, antimony gives you the syntax for ODEs. The antimony syntax is, if I want to write d by dt equals something, I use a prime. So T prime equals minus beta star V star T is exactly d by dt equals minus beta VT. So the next exercise is, and I said 4 ODEs, other 4 ODEs, would be to write the antimony strings for these 4, the I1, the I2, the D, and the V. So just following this notation, instead of T prime, you'd have I1 prime. So that should take about 30 seconds to do. If there's something confusing about it, then please let me know, and I'm happy to explain. mean, the nicest thing, of course, is when the paper has both the arrow diagrams and the ODEs. In that case, you don't have to do this work by hand. But an unfortunate number of papers only have one or the other. And so it's important to get familiar with that. And I'll do my best to warn people when there are inconsistencies in notation. When we used Herbert's textbook more in previous years, before last year, his book, his book was actually inconsistent. And so you had a situation where even within the same chapter, the notation was inconsistent. So we went through carefully and fixed all of that. But it certainly gave people lots of practice in this kind of interpretation. So here, it's pretty straightforward. I1 prime equals beta times V times T minus K I1, and so on. I don't think I need to go through all of those. But no matter how complicated the ODs are, you can always write them in this way. It's not really using the power of antimony very well. In particular, if I looked at the balance terms that I have, I'm having to write that. Well, these aren't the ones I was doing, but if I were going to write this one, I'd have to write this one twice, this one twice, this one twice, and so on. Okay. Now, if I start with arrows and I'm writing antimony, antimony was designed to write arrow diagrams in a simple way. So this is the thing we've had the most experience with, is translating an arrow diagram like this into an antimony string. T goes to I1 at a rate beta VT. T goes to I1, arrow I1, semicolon, beta times V times T. So that's straightforward. Notice that every arrow in my diagram has one line of antimony. So if I have this complicated arrow like I1 goes to I2 goes to D, that's going to give me 2 lines of antimony. Or nothing goes to V goes to nothing. That will also give me 2 lines of antimony. So the next little exercise is to take my arrow diagram here and turn that into antimony strings. And we can already count. We have 1, 2, 3, 4, 5 arrows. So you're going to have 5 antimony strings. One of the things you'll notice is that while you'll have 5 antimony strings and there are 5 ODEs, they don't correspond exactly because the way the terms are broken up is different in the antimony reaction strings from the way they're broken up in the ODEs. And I think the problem some people were having last week was that translation between those two can be a little bit tricky. Again, I'm doing these very simple examples so that you get some practice in a situation where you know what the answer is. And that way, when you have to look at a more complicated set of equations, you have more confidence in being able to do that. And again, if anyone needs help finishing this up, raise your hand. Josh and I are happy to help out. Does somebody need more time to do this? I don't want to go ahead until everybody's got it done. So. And I don't want to rush you. I just don't want people. If you're all sitting there done, I don't want you to be sitting there waiting. So if you need more time, say so. If you don't need more time, fill out the poll. Okay, so in this case, we have I1 goes to I2 at a rate KI1. I2 goes to D at a rate DI2. We get two lines for our V equation. Nothing goes to V at a rate P times I2. V goes to nothing at a rate C times V. Plus T goes to I1 at a rate beta VT. That gives us 5 lines. Now, if I start with arrow diagrams, it's easy to write arrows. If I start with ODEs, it takes a little bit more thought because I have to do some rearrangement of terms. I don't have to, but it's desirable to. So I can always use that prime notation that I showed you to write ODs directly. If I write nothing goes to X at a rate f of X, that's equivalent to writing dx by dt equals f of X. So I can write any ODE that way. If I write X goes to nothing, semicolon f of X, that's equivalent to writing dx by dt equals minus f of X. So I can also write any ODE that way. But if I have nothing on both, only one side of the arrow covered over, that means that I have to write balanced terms twice. And so if I see a set of equations like the ones we've been working with, where I have a series of balanced terms, like these, I can save a lot of pixels, I guess, by putting them in single equations. And so now what I'd like you to do is look at these 5 ODEs and write the corresponding antimony strings for them. And in some sense, this is a cheat because it's essentially what you just did. But maybe try not looking back at what you did, but trying to do it again, just looking at the ODEs. And again, the key thing here is to look for balance terms like this one to this one and this one to this one. And remember that that means that you have an arrow going from T to I1. This means you have an arrow going from I1 to I2 and an arrow going from I2 to D. Again, there's nothing wrong with breaking it up and writing more ODE fragments if you want, but it's more antimony-like to try to write transformations in balance form. Okay, so why don't people do that one? Okay. Does somebody need more time? Somebody hasn't expressed themselves, so if you need more time, say so. If you're done, please say so. If you've walked away from the computer, that's all right too, although it makes it harder for me to keep track of who's completing the exercises. Okay. If I use the notation for ODEs, nothing goes to T, rate minus beta VT. Nothing goes to I1, rate beta VT minus KI1. Nothing goes to I2, KI1 minus DI2. Nothing goes to D, rate DI2. Nothing goes to V, rate P times I2 minus CV. That is perfectly legitimate, but essentially I've just written the ODEs with the nothing goes to instead of variable prime equals. The more transformational approach would be to actually note the balance terms. T goes to I run at rate beta VT. So in that case, that term, this one term here, corresponds to this and this. this term and this term correspond to this one term here. This term and this term correspond to this one term here. So it's more compact to write it as a reaction. On the other hand, nothing goes to V isn't really what's happening. I have virus produced by my I2s and destroyed by decay. And so really, this should be broken up into two reactions, the production of V and the destruction of V. And so I still have 5 lines for each one of them, but the way the terms are arranged is quite different. And again, as long as you get the right answer, when you do the simulation, it's okay. But some of these are a little bit more flexible. Some of them make the logic of what you're doing a little clearer. And when I had people sending me their Python notebooks, their Jupyter notebooks, and there were problems with them, if they're written, if you write things in this form here, it's easier for me to analyze what's wrong. If you write it in the other forms, it takes a little bit more work to try to figure out what's going on. Again, it's a matter of taste to some extent how you do it. Okay. The next one is going the other direction. Everything we've done so far has been going from ODEs or arrow diagrams to antimony. It is a useful skill to be able to go backwards and take an antimony string and write out what the ODs are from it. In general, I'm asking you to put the ODs in text block above your Jupyter, in your Jupyter notebook, above the antimony version of it. But sometimes people aren't so considerate as you are, and you just get a big blob of antimony. You have to try to figure out what it means. In fact, there are some conversion tools available for antimony and for some of the other SPML solvers that will take your antimony string and actually turn it into ODEs and format it as TeX or Word document or MATLAB or something else. And you can look those up if you want them. There are even ones that will lay it out as a diagram, an arrow diagram with nice arrows and circles and things like that. But for the moment, we're going to do it by hand. And what I want you to do is look at this set of antimony code that I've written here on the right. Nothing goes to A, rate K1, A goes to B, rate K2 times A, and so on. And let's just do one term of it. The first term, J0, nothing goes to A. Nothing goes to A is equivalent to dA by dt equals, A is on the right, so the sign is positive. So this line here is just equivalent to writing dA by dt equals K1. J1, A goes to B at a rate K2 times A. A is on the left, which means dA by dt is equal to minus K2A. And this gives me also a term for B, dB by dt equals plus K2A because B is on the right. Now I have two terms for A, dA by dt equals K1, dA by dt equals minus K2A. So if I want the total set of equation for A, I have to add those up. So this pair of lines here gives me dA by dt equals K1 minus K2A. So the ODE, I have to look at multiple terms in my antimony to get my ODE for A. In principle, if I had A at the beginning or end of 25 different arrows, I would have 25 different terms in my ODE for A. And so I have to systematically look through every place a variable occurs in my antimony each time it occurs on one end or the other of an arrow, I have a new term in my ODEs. And when you're doing chemical reactions, it's quite possible for the same letter, and I'm not doing that for you today, but it's quite possible to have something that looks like, for example, sorry, still getting used to my drawing tablet here. It's possible to have something like 3A plus B goes to A plus C. And in that case, you actually have to be a little more careful. You have 3A used up on the left, 1A created on the right. So there's a net of minus 2A times whatever the rate is up here. Fortunately for us right at the moment, we're not going to run into that too often. But if we were doing chemical reactions, that's something you would run into. So that's another complexity. If the same letter occurs on both sides, you have to know what to do with it. But now, why don't people just write, for this stack of equations here, why don't you write the remaining? I've got dA by dt equals this. Write for dB, dC, dD, dE, dF. Once you've done one or two, it's going to be pretty obvious what the other ones look like, but why don't we go through that? And I recognize that some of these exercises may seem pretty dull, but I want to go through very simple cases first before we go to something fancier. Because if you have a diagram with 50 components and lots of different arrows combining things together, the bookkeeping can get to be, the individual things you're doing are no more complicated, but the bookkeeping can get pretty fierce. And I actually introduced this particular example because it's something that I wanted to, it answers a question that was brought up, I think, by Kali, or maybe Mercedes the other day. It's a partial answer. I don't have a complete answer, but it's a partial answer to the question that was asked. This happens to be called a cascade chemical reaction. And it's relatively common in biology to have reactions that look like that. It's a little bit surprising, maybe, but relatively common. Okay. Does anybody need more time with that? Okay. Okay. So just systematically, dA by dt, K1 minus A2, dB by dt, K2A minus K3B. And so if I look here, that first equation, generates, first equation generates a balance here, second one balance here, third balance here, fourth balance here, fifth balance here. Notice that if I added everything up, if I summed everything, I would get K minus K7F. Everything else would cancel out. And that tells me that the equilibrium amount of F, if I were to let this run to steady state, would be K1 over K7. Which is again of significance if you're doing biochemistry, but also be significance in the equations we've been writing where we have birth and death. It gives us the equilibrium population. That's right. We haven't talked about steady states very much, but that's a little bit of a heads up on steady states. Okay. So the other thing we can do with this would be to write arrow diagrams. Converting antibody to an arrow diagram, if we use the reaction notation, is pretty trivial. You simply take the thing that is on the, I've given you the answer. I would take myself away. You take the thing that's on the right-hand side of the semicolon and you put it over the arrow. So basically just move it here. And then you can combine your arrows into one big long line. So why don't you write quickly the arrow diagram for this stack of equations, which is pretty simple. And I think when you've done that, you've done everything, all the possible permutations. You've taken arrows and turned them into ODs. You've taken arrows and turned them into antimony. You've taken ODs and turned them into arrows. You've taken ODs and turned them into antimony. You've taken antimony and turned them into arrows. And you've taken antimony and turned it into ODs. So all of those triangular relationships, all those 6 directions you've done. Again, very often the rate equations may be more complicated than here, where it's just a simple first-order linear equation. You might have A plus B goes to C plus D, or even 3A plus 2B goes to C, 7A plus 6D. Those are all possible. And so in those cases, you have to be a little more careful about your bookkeeping. But fundamentally, what you're doing isn't any more complicated. All of the translations that we've done here cover the things that you need to do. Does anybody need more time? So here, it's called a cascade reaction because A goes to B, goes to C, goes to D, goes to E, goes to F, goes to nothing. And you simply write the rate laws on top of the arrows in the appropriate places. Now I want to talk a little bit about something that came up in the examples that were given before in some of the projects, which is what are called delay differential equations. We've seen equations that look like di by dt is some function of stuff, but that stuff was being evaluated now. And occasionally, especially if you're dealing with things like the immune system, or for that matter, births, you'll have an equation where di by dt is equal to some function or some variable evaluated not now, but sometime in the past. The number of births today is equal to the number of pregnancies 9 months ago, modulo deaths and some variation. The number of deaths from COVID may be the number of infections from COVID 3 weeks ago times something. Or in the case of the immune system, the number of antigen-presenting cells in the lymph node is related to the number of antigen-presenting cells in the tissue 2 days earlier. And so it's very natural to write ODEs where the variables are evaluated not all at the same time, but at previous times. And those are called delay differential equations. And there's a fundamental problem with delay differential equations, which is if I have the kind of ODEs we've been dealing with so far, all those rate laws on the right-hand side depend on the values of my variables now. If there's a delay, then di by dt equals x of t minus tau depends not just on the value of x at t minus tau, it depends on the value of x all the way between times minus tau and 0. So instead of depending on a single value, it depends on a continuous infinity of values. And that means fundamentally, even though the equation looks like one-dimensional equation, it's actually an infinite dimensional equation. And it can be turned into partial differential equations or into integral differential equations. And so delay differential equations are deceptive because they look very simple, but in fact, they're very hard to evaluate. And in fact, there are no universal numerical solvers for delay differential equations. MATLAB has some packages, some extension packages that are pretty good at solving delay differential equations of simple kinds. And Mathematica will do it under certain circumstances. Although when you use Mathematica, you sometimes have to be careful. It's probably much better than it used to be. But if you typed equations into Mathematica and asked it to solve them, it would happily give you solutions which were often wrong. And it wouldn't warn you that it didn't know what to do and had thrown something that was meaningless. I remember when I used to use Mathematica a lot, which was 15 or 20 years ago, it would happily give you answers which were wrong and not warn you about it. Antimony, for better or worse, takes the strategy that since it can't solve arbitrary delay equations, it won't solve delay equations. And that makes life a little bit awkward if somebody has a project paper which has a delay in it. And if you look at people like Alan Perlson's papers, he writes very simple equations with delays. And they're not so simple because of those delays. And so one way you can deal with this is an approximation. It's not a very good one, but it works okay. And you can formally make it into something that's perfect if you want to do the math. You can look it up. I'm not going to do the full math now. But it uses the equations we've just written down. And what it's called is the Bucket Brigade. Suppose that I have K1, and K1 now is not a parameter by itself, but is actually some variable that I'm forcing. And I want to know, I say that I want to write, let me see if I can do it, df by dt, df by dt is equal to K1 of t minus tau. Right? If I write a stack cascade reaction of the kind that I have, I can think of this as the amount of material in K1 is being passed to variable A. It's being passed from A to B. It's being passed from B to C. It's being passed from C to D. It's being passed from D to E. It's being passed from E to F. And F, it's going away eventually. And that's called the Bucket Brigade. You can think of it as water being passed from one person to the next person, to the next person, to the next person, to the next person, to the next person. What happens at the end is a little problematic. In this case, it seems that buckets are piling up at the end. If I didn't have this decay term here, that would correspond to this picture here. And I'd wind up with an arbitrary amount of water at the end. So I have to think a little bit about what I do with the end term, but that's a start. And the delay of a stack like this is approximately 1 over K1 plus 1 over K2 plus 1 over K3 plus 1 over K4. Okay, so let's write a little version of this. You've got your antimony. So now I'm actually going to ask you to launch Tellurium on NanoHub to do this. And remember events. So we used a concept of events in antimony, and the syntax for an event was at parenthesis, and we're going to be doing things in terms of time. So you could say at time greater than 10, colon, I don't know, K1 equals 1, something like that. Okay, that would work. And so what I want you to do, well, first I'll show you a little bit more and then we'll do this together. What I want to do is we're going to make K1 start at 0. We're going to have it go up gradually to 1. We're going to have it stop at 1 for a while, and then it's going to go down again. And then we're going to see what happens to the value of F at the end of the stack. And ask the question, is F a reasonable approximation to K1 at some past time? Is that clear? So what I want you to do now is write the equations we have here in antimony. Just plot K1 and F. And start out with all of your K, K2, K3, K4, K5, K6, K7 equal to 1. And so you'll have to write a little event rule. And let me just, maybe it's maybe it would be helpful actually if I had one extra term here, because I want K1 to increase slowly. So you could add a term that is, I'll turn on my pen. So you can add a term, I don't know, we could call it J. It would be J minus 1, which I'm not allowed to write. So let me just call it J, colon, and we'll say nothing goes to K1 at a rate K0. And if I start out with K0 equals 0, that gives me my first part there. And I'll give you the result, the way to get started here. You'll say at time greater than 10, K0 equals 1. Now you can figure out what to do for the rest of it, okay? Is that clear? Josh, did that make sense? Okay, so now this is a little bit of an exercise, and see whether people are able to do that. And again, a full exploration of delay equations and how to implement delays is actually pretty demanding. But this will give you enough that if you see a delay in a set of ODs you want to replicate from a paper, you should be able to at least get the basics down, and then you can look up the details. Again, in this class, I don't think I'm going to have time to go into all of the subtleties of implementing delay equations. But this is a quick and dirty way to get an approximate delay equation to work. And by the way, I should have actually, I did myself a disservice here. I want K0 to be 0.1 rather than 1. If you make it 1, it won't work. You'll see you'll see one of the reasons that delay equations are a pain if you make it 1. If you make it 0.1, you'll find out why. Well, you'll see. Okay, is the little assignment clear? Any questions about that? Great. I'll give you a few minutes to work on that. Okay, so if people who are done, why don't you, we're a little late for our break, so why don't we take a 5-minute break? And whoever is still, okay, everybody's done? How'd it go? Let's look at the results. Show you what I got, and you can tell me what you got. This is what I got. So I used an @ to turn on K0 at time 10. I kept it on for 10 units of time. I then had it turned off again to keep K1 constant for 40 units of time, and then had it go down to 0 again over 10 units of time. So my K0 is this trapezoidal function. 0 goes up linearly, stays at a maximum, then goes down again. And my output of F is a little bit curved at the corners, but it's delayed with respect to K1. And exactly what that delay is something we could study. It's about 7 time units.
James, one question. So,
yes.
What would be the difference between doing this and doing K1 goes to F, and then have like let's say a K that is the additive of all these K1, K2, K3, K4, K5, K6, K7.
Okay, that's a good point. So let's try that. So effectively, that would be plotting A as a function of instead of plotting F, that would be the first one in my stack, and then changing the parameter value, right? So let's do that. Let me plot A instead of F. And it still matches, but the delay is short. Now let me plot B instead of A, because A is sort of special. Let's plot B instead of A. Doesn't look too bad. Now let's try to get the delay bigger by making K2 small. If I make K2 small, let's make it 0.1. So I'm trying to make it 10 times bigger. What happens? I get that. So I do get some delay at the beginning, but the shape of my curve doesn't match.
I guess the question is, because you multiply it by 10, but what if it's just the sum of all of those Ks?
Well, so the sum of my Ks was 1, 2, 3, 4, 5, 6, 6. So I'll make it 6. And it actually should be the reciprocal. So it should actually be less than 1 rather than bigger than 1. But let's see, where was it? Which one was it? K1? Mm-hmm. K2, sorry. So it'd be 1/6. So right. It'd be 0.16.
Okay.
I mean, it's not appalling. I could rescale the maximum to make it match. But it's much fuzzier, mm-hmm. and it doesn't have a uniform value at the top. So the more stages I include, the better the result is. So if I really only care about the delay and I don't care about anything else, using 1 or 2 stages is fine. If I wanted to track very carefully, then the more stages I add, the cleaner it will be. So those are very good questions. And so I would encourage people to play with this. As I mentioned, this is not something that we're going to be able to go, at least now, go into in complete detail. It's a topic of interest. But I did want to show people at least a little bit of how you can make this work, so that if somebody had a delay equation, they could get started with it. And if you really want more detail on delay equations, there are lots of articles on how to implement them. But at least this gives you this kind of bucket brigade is the standard way to do it. And as I added levels, if I had F goes to G, G goes to H, H goes to I goes to J, then these rounded corners would get sharper as I do it. Exactly how you control the delay and how you control other things requires a little bit of math, which I don't want to do today. All right. So having said that, we were going to do our break. So why don't we do our break now, if that's okay with people? And let's say 6:45. Let's come back at 6:52. 5-minute break, all right, for people? Unless people don't want, if people don't want a break, it's all right, but I think everybody needs some break. Otherwise, it's a long sit. Okay, 6:52. Let's see. But it's not trivial to optimize that, Josh. It actually, if you play with that example, you'll find out that it's not so simple to get it to work. If you write the mathematics, then you can figure out how you have to change. You can't just change the K's independently. You have to change them all at the same time in the right way to make it work. But for short delays, this isn't too bad.
boy, that's not fun. Why does it take so much time? Like, I don't know. Have we get this as soon as we can drink?
Okay, are people back? Ready to get going again? Okay. So, courtesy of Josh, we have another exercise. And this one is going to be purely a antimony writing exercise, although you should be prepared that this antimony writing exercise in class will turn into a homework problem. So it's we're not trying to waste your time on it. This is a model of within host malaria replication. And of course, it's not a virus. Malaria is a eukaryotic parasite. Has some very strange properties. Actually, bad as viruses and bacteria are, eukaryotic parasites are much more insidious. The worst one probably that we run into relatively frequently is Toxoplasma gondii, which you get from cats, and which attacks your brain and causes permanent changes in brain and behavior, including increased aggression, among other things. One of the interesting things is that there's some populations in the world where it's very prevalent, where 60, 70% of the population have it. And it's also untreatable, which doesn't make it very pleasant. But in this case, it's a model for malaria. And the first step is to take this model for malaria and turn it into an antimony string. And the one thing that you have to be reminded of, perhaps, given the labeling, is that this arrow here with the lollipop on the end is a regulatory arrow, which means that M is not used up. M is only acting to regulate the reaction U goes to P. And if you look carefully, you can see that I actually photoshopped in that ending of the arrow because the way it was printed in the original paper was inconsistent. So is it clear what the little assignment is? So it's to take this diagram here and turn it into an antimony string. I'd like everybody to take a few minutes and do that. Clearly you have 1, 2, 3 species, but you have a lot more than 3 arrows. You have 1, 2, 3, 4, 5 transformational arrows. The regulatory arrow, and this is a hint, doesn't actually generate an arrow in an antimony string. So why don't you give that a shot? And if you get done early, as a heads up for the homework, if you want to start coding it into antimony and tellurium, that would be great. But we're not going to do that in class now. But so you don't wind up, I don't want you people to be sitting waiting for everybody. I want people to take the amount of time they need to solve a problem. But I also like to give a little bit of a work ahead for people who get the problem done a little bit faster, so that they don't have to sit too much either. You also notice that his notation is somewhat different in the sense that he's using the Roman U, UM, and M for species amounts, not using the italic version. So I typically use the Roman for the species name and the italic for the species amount. But that's not something you can count on consistently in the literature. Does anybody need more time? So again, there are 1, 2, 3, 4, 5 arrows, so they're going to be 5 lines. Nothing goes to U at rate lambda L. U goes to nothing at rate mu times U. U goes to P at rate beta UM. P goes to M at rate RAP. M goes to nothing at rate DM. And this regulatory arrow doesn't generate anything. Is that what people got? Everybody got something similar to that? Okay. So that's a typo. The next assignment was supposed to be, sorry about the typo. The next thing was to convert them to ODEs. So can you write the equivalent ODEs for this arrow diagram? And I apologize if there's a typo on the slide. Well, that's the answer. So you've seen it. You can. If you have photographic memory, you know what it is. So this should have been. This should have been. You'll note that you'll have 3 ODEs, 1 for each species. So in this case, the ODs are a little more compact than the arrow diagram. And you'll get multiple terms. For example, for U, you'll have three terms because you have one arrow pointing in and two arrows pointing out. So your du equation will have three terms. For P, you have one arrow pointing in, one out. So your P equation will have two terms. M, you have one arrow pointing in, one arrow pointing out. So your M equation will have two terms. Does anybody need more time, or is that okay for people? Okay, so we have three equations as promised. Du dt equals lambda from here, minus mu u from here, minus b um, beta um from here. There's a balance term. Again, we see this structure of balance terms. So we have this and this, one balance term. We have P here, a second balance term. And so there are two balance terms. All right. So now I'd like to come back to where we were 2 weeks ago and resume our discussion of viral infection. And I want to remind you that when we're doing these in-host virus models, we're actually talking about a quite complicated set of biological processes. And the models that we've looked at, even the most elaborate models we'll look at, are still enormous oversimplifications of the reality of the immune response. And to some extent, nobody can really model a human immune response very effectively. We would love to be able to do that. And my hope is that as we dig into diseases like COVID, we can begin to understand the immune response better. This is one of Sam's slides talking about the adaptive immune response. And the key thing that happens in the adaptive immune response is that you have the phases of the adaptive immune response. Here, we're talking about a lung infection or perhaps a blood infection. The virus binds to epithelial cells, cells that are in the sheet, exposed to the environment in some way. Now the virus comes into the cells and begins to replicate. Those cells produce cytokines. Those cytokines are signals that tell, biochemical signals that tell the system that there is an infection. That would be true both for bacterial and for viral infections, although which cytokines are produced would be different probably. And it primes what are listed here as immature dendritic cells. Those are sentinel cells that are present in your tissues all the time. Those sentinel cells mature, and one of the things that they do is they pick up fragments of dead cells and virus. When they do that, they actually crawl through the lymphatic system. Everyone is familiar with blood vessels, but there's a second network of vessels called the lymph vessels, lymphatics, that are in many ways analogous to the blood vessels that carry lymph rather than blood. And the immune cells move through those to the lymph nodes. Once in the lymph nodes, they stimulate production of T cells, targeted T cells that will target the virus, and also B cells which produce antibodies. And then those cytotoxic T cells, the CTLs, and the antibodies are returned via the blood to the tissue. Things are a little more complicated because there are more cell types and more signals, but that's the basic idea. The text that gives you a little bit more detail. There are quite a few steps here. There are quite a few molecular species, and there are quite a few processes, but that's the basic thing. And the key issues in modeling this are that this step takes time, days. And once you're in the lymph node, the production of T cells by replication takes days. The T cells getting back to the tissue takes time, but it's in the minutes rather than the days. And so the key delay, which is that your adaptive immune system takes a week to 10 days to turn on, comes about because of this time delay and the replication time delay here. And as you get older, both of those times go up, so your adaptive immune system takes longer to respond. If you've been exposed to the virus before, then the T cells are already present, and so you save this delay, so you don't have this delay here. And you also have antibodies present, so those help deal with the virus. And the reason that people can be treated with blood antibodies drawn from people who've been exposed to COVID, or with these monoclonals that have been used by Regeneron, is because the antibodies are pretty effective at gumming up the virus and preventing it from infecting and spreading. However, we have to, if we want to model that, the natural thing to do, and this is why delay equations show up rather early in these things, is that the time for the dendritic cell to get from here to here is often represented by a delay. And we're going to have to work our way around that in our models. So coming back to our basic viral decay model, we had, I believe, finished the model that we had here. One of the things we had to talk about was how long the virus lasts in the extracellular space. It lasts on the order of 2 to 3 hours. We measure everything in units of days. So 2.4 hours would be a tenth of it, would be 10 per day. 2.5 hours is 9.4 per day. And so we talked a little bit about some of these processes, the same ones that I've just shown in that diagram. There are a whole series of things that one can work on. For example, Josh has been working on how cells recognize that they're infected and what they do when they do that. One of the things that cells do, we've talked about cytokines, which are primarily long-range signals to the immune system. Interferons are innate immune responses that are local to the tissue for the most part. And they send local signals from cell to cell saying that there's a virus or a bacterium in the vicinity. And one of the ways cells respond to interferons is by blocking viral replication within the individual cells. And they also respond by killing themselves. One of the groups in Scotland and St. Andrews University has just published some very nice models of how cells kill themselves by apoptosis. And when we put that together, and this is the model we've been working with, just translating it back and forth, we were able to replicate several of the stages that are observed actually in the viral load. So we were able to replicate the initial delay in virus production, the exponential ramp up of the virus, this is for influenza, and then the saturation and the gradual decay of the viral concentration due to the innate immune system. And so this simple model that we wrote down here with the more or less guessed at parameters that we picked here actually replicates the first phases of the viral load quite well. What it doesn't do is give us this clearance in phase 5. And that clearance in phase 5 is due to the adaptive immune system. And we're going to have to do a lot more work to get a rough approximation to that clearance result than we had to do for all of the other phases put together. And unfortunately, that corresponds to the reality that the adaptive immune response is not local to the tissue, and it's relatively complicated. It involves a lot of different biological effects. So if we look a little bit more detail at what's happening in the adaptive immune system, and again, this is a slide from Sam. There are a bunch of different locales where immunity is generated. You have what's called the humoral response, where B cells, this is typically not for a primary infection, but when you see the cells, when you see this infection a second time, when you see or exposed a second time to a virus, your body will have created B cells that have antibodies on their surface that recognize that virus. When those B cells, which are acting as memory for immune system, run into the virus, they replicate, and they also begin to churn out additional antibody. And that additional antibody then sticks to the virus and helps eliminate it. And one of the big questions when they asked the question, did a vaccine lead to long-term immunity? This is what they're measuring. The vaccine will stimulate the production of B cells that target the particular antigen that's in the vaccine. And then they'll measure the level of antibody in your blood as a function of time. And if they do a challenge experiment where they expose you to the virus, they'll ask the question, how much new antibody is being produced? And they'll ask the question, how does the antibody level decrease in time? Because as time goes on, these B cells, these plasma cells die. They stop producing antibody. The B cells gradually die off, and your body forgets its immunity. Your body has a limited capacity to respond to viruses, and so it tends to keep the viruses that you've been exposed to most recently at the top of its stack and downregulate its production of responses to others. With T cells, the early phases of this, again, are happening typically in childhood and adolescence, which are the production of the precursors of the T cells in the bone marrow. They migrate to the thymus. The thymus, in turn, filters them to make sure that they're not anti-self, because if you produce T cells that target your own cells, you're in trouble. Then they are released to the lymph node where they're stored and banked, essentially, until an antigen presenting cell comes to activate them. Once they're activated, then they move back to the tissue. Some of them become what are called memory T cells and provide, again, a faster response once you're exposed, once you've been exposed. Okay. That basically would be. The key thing that's happening in the adaptive immune system, again, is that when the infected cells die, they release what are called apoptotic bodies. Those apoptotic bodies are phagocytosed by these cells that are going to become antigen-presenting cells, primarily macrophages. Those macrophages then move to the lymph nodes to activate T cells. And so the key things that we have to know is that there are two signals, that at least two signals coming from the tissue. There's a cytokine signal, which gets to the lymph nodes quite quickly. There are the antigen-presenting cells that take longer to migrate. The terminology is a little bit confused. You'll see macrophage, you'll see dendritic cell, and you'll see antigen-presenting cells. And depending on who's writing about what, those could all be the same cell. And so as people have learned more about the immune system, the terminology has gotten more complicated, but sometimes the old terminology is still used. So we have to live with that. Those antigen-presenting cells will activate T cells in the lymph nodes, which will then replicate, causing your lymph nodes to swell up. And those T cells will then get into the blood, or here afferent lymphatic through the lymph system as well, into the blood, go through the bloodstream, get to the tissue, and then do their job of killing the infected cells they target. They will also kill uninfected cells that are near the cells that they target. And so one of the problems is that to get rid of the infection, you have to kill your body's cells, the infected ones, and you have to make a fire break around it. And that fire break sometimes gets to be too big and can cause major damage. Okay. So we have to now try to start building some understanding of what we're going to do with the immune system. And we talked about this a little bit a couple of weeks ago, but since it's so long ago, I want to go back over it. And we're going to think about the functional relations that we need in terms of this idea of limiting cases. And the first thing that we're going to talk about is, if we don't know what the rate laws should be, what happens? Can we make at least an educated guess about what happens when, for example, there are no cytokines? If there are no cytokines, then we don't expect to be producing many T cells. Whether we produce absolutely no T cells or some T cells is a question we might want to investigate, but we certainly don't expect there to be many T cells. If there's no signal from our tissue that we have an infection, we don't want our immune system turning out a lot of cells that are going around killing other cells. And so basically, for the case, for example, of cytokine levels being very low, we expect that the production of T cells will be very low, which means that our limiting case would be this bottom left-hand corner. Whether for very small values of cytokine we expect to produce some T cells or no T cells is something we have to think about. But as a reasonable first step, you might assume that even if the cytokine levels are fairly low, you're going to produce some T cells. The other thing we have to think about, and this could be true also in our model here, in our diagram where we haven't labeled the rates, is some basic things which are in chemistry typically called mass action. So if we have these susceptible cells becoming I1 cells, and there's no virus in the environment, we can't have any infection at all. So if the level of virus is 0, the level of infection ought to be 0. Similarly, if we have no early infected cells, the number of late infected cells we get should be 0, exactly. And if we have no late infected cells, those cells can't die, so the rate of death of I2 cells should also be 0. Similarly, if there are no infected cells, they can't produce any virus. And the simplest way of getting all of those things is to have linear results, which is if the rate at which I1 becomes I2 is K times I1, that clearly goes to 0 when I1 is 0. What happens when I1 is very large is another question, but at least at the limit of small I1, we expect it to be linear. If that slope at 0 were 0, then things are a little more complicated. But for a transition like I1 goes to I2, you expect it to be independent from each cell to every other cell, and so linearity is reasonable. Okay. Now, the next thing to do is to think about what happens when you have a lot of something. In the case of I1s becoming I2s, they're independent of each other, so you don't expect that the rate will go down if you have a lot of I1s. On the other hand, if you have some process that's stimulated by chemical, so for example, the rate of production of T cells as a function of cytokine level, there's some maximum rate at which you can produce T cells. The lymph nodes have a maximal capacity. And so if the cytokine level goes high enough to give you the maximal capacity, increasing the cytokine level more won't increase the rate at which you produce T cells because it's saturated. And so in that case, the simplest thing you get is something like this picture here, where suppose the parameter is the amount of cytokine, the value is the rate of production of T cells. If I have a small amount of cytokine, as I increase the amount of cytokine, the rate of production of T cells goes up. If I have a lot of cytokine, the rate of T cells is production of T cells, whatever the maximum possible rate is. And so you get this curve that looks like this. It's got some slope at 0, and it reaches a maximum value. It's called saturation. And that's pretty typical, and we'll see that again and again. There's a simple functional form, which we went over the other day, and I failed to correct a typo in this, actually. The typo is not in the equation here. The typo is in this statement here of B, which is called the Michaelis form. These are all equations that were derived in the context of chemistry. There's no particular reason that the functional forms that apply to chemical reactions should apply to biology, but it happens that mathematically the structures are reasonable. And in this case, the rate of, if I want to know what this value is here as a function of my parameter, if my parameter is x, if I write f of x is equal to v times kx over k plus x, then if k is very small, if x is very small, then the denominator here looks like k, and I'm left with v times x. If x is very big, the denominator looks like x, and I'm left with v times k. And so my saturation value is v times k. My slope at 0 is v, and the value at which I get to half of the maximum is when x equals k. There are other possibilities for getting this kind of saturation curve. If I want it to be decreasing, there are other forms, and we went over some of those before. The key thing about these is always there's a maximum value at infinity, the slope is 0 at infinity, the value is 0 at 0, and the slope is maximal at 0. One of the things that we're going to find out a little bit later is that our T cells when they go into tissue, take time to kill their targets. And that means for a given number of T cells, the rate at which I can kill infected cells is limited by the number of T cells. And that's going to be an issue. It's actually a big issue in the way your body clears disease. And so this kind of what are called Michaelis forms are going to be typical processes that show saturation. I recommend that you write rate law so that these saturation terms look like go between 0 and 1 as a function of x. That would mean dividing through by k. And the example I think I gave a couple of weeks ago was, again, the T cell example. Each T cell takes about 40 minutes to kill its target. So one T cell can kill about 30 to 40 target cells a day. So that means you need a lot of T cells in your tissue if you want to clean up a lot of infected cells. The other functional form that we'll run into a lot, and here it is written correctly where x is normalized by k, is called a Hill function. A Hill function is a good way of quantifying what we don't know. And it has the following properties. It looks like my Michaelis function. It's a velocity, a maximum velocity, times, and here we'll normalize by the half maximal value, makes life easier. X over k, it's raised to the nth power, divided by 0.5 to the n, plus x over k to the n. And now we have two parameters. We have k and we have x. All of these have a sigmoid form, provided that n is bigger than 1. If n is but 1, we recover the Michaelis form. They all have the property that when x is equal to a k, f of x is a half, which is nice. They all have the property that they're 0 at 0. They all have the property that at infinity they go to 1. And the bigger n is, the steeper that transition is. If n is bigger than 1, the slope at 0 is 0. And so you get what is called a sigmoid. And Hill functions are used a lot in approximating relationships where we don't have a lot of detail. We can turn an increasing Hill function into a decreasing Hill function by replacing the numerator here by a 1. And in that case, our value is 1 when the s is 0, and it decreases to a half when s equals k, and goes to 0 as s gets large. And so you always have this pair of increasing and decreasing Hill functions. Again, if you want to go to the Michaelis limit, you just take n to 1. So when you're going to think about a problem where you don't know much, there's always this set of questions that you ask. The first thing is, whatever the thing is a function of, parameter or variable, you say if that parameter is 0, what happens? Is the value of the thing that I care about 0 or non-zero? Is its slope at 0, 0 or increasing? If its value is 0, or if it's finite, is it increasing, decreasing, or at 0? There's some possibilities that you don't run into very often, but are possible. The slope could be infinite at 0. That's allowed. Increasing or decreasing. So for example, 1 over x is a perfectly well-behaved function, but it has a slope of minus infinity at 0. So you don't want the value at 0 to be used. And then you also think about at the upper end, does the value saturate or not? And what is the slope at saturation? And there's quite a bit you can think about these problems. I've got some slides that go into this in a lot of detail. I don't want to go into a lot of detail here. But when we begin to build models where we don't know what the real functional forms are, this kind of argument gives us a place to start. Okay. So let's come back and talk a little bit more about the biology. When cells are infected, they know it. When there's virus in the neighborhood, cells do also sometimes know it. Cells can have on their surface receptors. There are a whole variety of these. Those receptors can attach to, if you're lucky, either antibody-bound virus or to the virus fragments. And they send signals which have this PAMP response. And the cell can respond to those signals by doing a lot of things. It can block cell membrane fusion, which basically keeps the virus out of the cell entirely. It can block the replication of the viral DNA or RNA, depending on what kind of virus it is inside the cell. And it can also block the production of viral proteins and also the release of the virus. Clearly, these things aren't completely effective, otherwise the virus would never get around and cause a problem. But your cells do have a whole array of antiviral responses which they use. There are a whole bunch of different ones. And here's some of the things that can trigger these pathogen-associated molecular patterns. The first are bacterials. Lipopolysaccharides and bacterial cell walls are related to bacteria. Double-stranded RNA in the cytoplasm. RNA is normally single-stranded. And cells, when they see double-stranded RNA, which is associated typically with viral genomes, notice it and respond very strongly to it. Unfortunately for us, SARS-CoV-2 is a single-stranded RNA virus. So that means there's nothing special about the RNA to trigger the cell to have a bad response. The other thing that cells don't like is DNA, especially single-stranded DNA in the cytoplasm. And so diseases like HIV produce that. SARS-CoV-2 is a single-stranded RNA-positive virus, which means it goes RNA to RNA single-stranded, and that doesn't trigger that. However, there are some other things that it does trigger. These pattern recognition receptors, there are two particular families of those, the toll-like receptors and Rig-I receptors. Josh is working on those. And all of these trigger the production of cytokines and interferons. The pathways can get almost baroque in their complexity, but actually it's not quite as bad as it seems. The ones we care about here are going to be the single-stranded RNA ones, because we're talking about SARS-CoV-2. Here, the virus could bind to a receptor on the surface of the cell. Here's a toll-like receptor. These are some other ones. And that can send a signal that the cell is causing a problem. Has a problem. Here, the single-stranded RNA triggers toll-like receptor 7 in an endosome. Through toll-like receptor 7, there's a long cascade of signals that produce interferon, also inflammatory cytokines. Rig-I is another pathway that's associated with this. The details, molecular details, we're not going to worry about at the moment. There are other places that these things can happen when the virus starts being producing its proteins and assembling. It uses the endoplasmic reticulum and the Golgi apparatus. And the Golgi apparatus and the endoplasmic reticulum have their own signaling mechanisms to know when there's something wrong. And so they can also signal for these problems. And one of the things that we run into, we're not going to model now, but Josh has to worry about, is that there's something a little bit funny about how the interferon response works in cells. The cell that's infected produces interferon, which is down here, interferon A. It releases it into the environment, and then other cells bind that interferon and send a signal. Happens to be through JAK-STAT pathway. And the cell can respond to its own signal. And so one of the things that's sort of funny is that the interferon that's produced in the cell directly, it has to leave the cell and come back through a pathway to act. And that can cause some complications. Viruses, if all of these defense mechanisms work perfectly, you wouldn't get infected. The infections would be blocked. And in Josh's simulations, he shows that if you turn interferon on enough, it can block the propagation of viruses in vitro. And that's actually observed in influenza. There is a particular protein produced by influenza, NS1. NS1 blocks interferon production by cells. If you take an influenza virus and you knock out the NS1 gene that produces NS1, the influenza virus can still infect cells. It can reproduce a little bit, but the tissue is able to produce enough interferon that it blocks the spread of the virus. And so without that particular protein to disable the interferon system, or at least knock down the interferon system, influenza couldn't spread. Exactly what's going on with SARS-CoV-2, I'm not sure. My guess is that if I read the literature more carefully in the past few weeks, they've identified what it is that's turning off interferon in SARS-CoV-2. Josh, maybe you can fill me in on that one if you want. Here is a list, again from Sam, talking about some of the ways that viruses block interferon production and signaling. Again, for the virus to survive, it has to do that. For us to survive, we have to resist that. And so there is an evolutionary arms race between viruses and their hosts, where the viruses try to get better and better at turning off the host defense system, and the hosts try to evolve around the virus. Of course, the viruses evolve faster than the host. The flip side, of course, is that evolutionarily, if the virus is too effective at killing off its host, and it only has one host, one definitive host, then the virus dies out. And that leads to what's called coevolution, where at least at some level, in certain cases, when a virus has been living with a host species for a very long time, it tends not to be non-lethal, but to be less lethal. In the particular case of SARS-CoV-2 in bats, SARS-CoV-2 seems to have been infecting bats for a very long time, and bats don't seem to get particularly sick from it. They seem to be able to carry it and survive pretty well. Okay. How cells respond, this is probably more molecular detail than we need. I liked Sam's slides a lot, so I took maybe more of them than I should, for today at least, because we're going to run out of time before we get back to our model, I think. Is that the cells have a particular set of receptors on their surface that respond to interferons, other ones that respond to interleukin 6. They both signal through the STAT pathway, different parts of the STAT pathway, and trigger a variety of responses. Interleukin 6 is, you're getting a lot of molecular species names without a lot of detail about why you should care about molecular species names. Most of the molecular species names that you're hearing today are ones you can forget very quickly. There are a few that you do need to remember, or at least that I recommend that you remember. Interferon alpha is type 1 interferons. Is something that you're going to hear about a lot. Sometimes there certainly are antiviral therapies that involve them. They're your cell's primary line of defense against early infection. If you have some kind of deficiency in interferon type 1, so interferon alpha response, you're extremely susceptible to viruses. You'll probably die from a viral infection. If we could trigger higher levels of interferon alpha response, we might be able to prevent the virus. It's not going to prevent you from getting infected, but it could prevent the virus from becoming very serious. Those act typically over the first day or two of infection. Interleukin 6 is the primary early cytokine for viral response. And the key thing about interleukin 6 is it's the first signal, major signal that goes to your lymph nodes. And it triggers massive inflammation. And so almost all of the symptoms that you get when you get sick from a virus are not from the virus. They're from interleukin 6. So when you get the flu and you feel like you've been run over by a steamroller, you get a terrible headache, you get a high fever, you get muscle aches, you can't move, you're sensitive to light, all of that is not the virus that's doing that to you. That's interleukin 6. And interleukin 6 actually is very correlated with body temperature. So when you get a high fever, your interleukin 6 levels have gone up. And so that's one of the primary early responders to virus. It also happens to have the property that you feel really sick when you have a high interleukin 6. And so when you feel sick, what you're noticing is interleukin 6 is going up. Okay. And here's a little slide talking about that. Interleukin 6, fever, fatigue, sleep. Also production of lymphocytes, so white blood cells, and eventually the production of adaptive immune cells. Okay, so we can skip this one. Another term that we probably need, chemokines. So cytokines are regulators of the immune system that typically act remotely in the lymph nodes. Chemokines are signals that act over shorter range that basically tell your body where the infection is. And so chemokines, for example, you have the immune cells moving in your blood. They have to stop moving in your bloodstream, bind to the wall of the blood vessel, go across the wall of the blood vessel and get into the tissue where they can start chewing up the infected cells. Chemokines are the main molecular species responsible for that. And exactly how that works and how that's modeled is very complicated. There are people who do it. So Roger Kam at MIT has spent many years building rather elaborate models of how that works. Okay. So now we're going to run out of time again, but let's get one more level of our model put together. So we're now going to talk about cytokine production. And the model that we're going to be working with, the one that we started a couple of weeks ago, and we're still working on now, does something which is rather unattractive, but was a simplification that I made when I wrote it down, which is that it's going to confuse the antigen-presenting cells and the cytokines. So what it's going to do is it's going to say that the infected tissue sends a signal to the lymph nodes to respond, and it's going to send one signal to the lymph nodes. And we're going to call that signal C. And the problem with that is that there are actually two signals, there are actually many, but the two main ones, that are interleukin 6, which gets the lymph nodes very fast, and the antigen-presenting cells, which take days to get there. And combining those two signals that operate on different time scales into one was not the greatest idea in the universe, although it's done by almost everybody who works in the business, which is not a very good excuse, but nevertheless is what we did. And so we're now going to assume that our infected cells, our I1 cells and our I2 cells, have noticed that they're infected, and they're going to start producing cytokines. And the cytokines are released, and the cytokines also are eliminated. And they're going to be eliminated in two ways. They're going to break down chemically, and they're also going to be eliminated by moving to the lymph nodes. And so we're now going to add to our species world a new equation, which is C, which is essentially our immune signal. And that's going to be produced by our infected 1 and infected 2 cells at a linear rate. And it's going to be broken down at some clearance rate, CC times C. And there's some things that are known about this. Cytokines typically have a lifetime in your body of about half a day, a little less. So the decay rate's about 2 per day. And the production rate isn't going to actually be meaningful because the only thing that's going to matter is the rate of production compared to the rate of response. But we'll assume for the moment, since we don't care about that number, we'll just say it's 1 per cell per day. Okay, and now we're going to be out of time. So next time, I promise, now that we've done all this background work, the next time we will start immediately here. What used to be exercise 8.1 is now going to be 10.1, building a model of cytokine production. And we'll start with that model of cytokine production. We'll then have the cytokines trigger the production of immune cells. Those immune cells will then migrate back to the tissue and kill the infected cells and clear the virus. And we're going to need all of those steps, unfortunately, to be able to get that clearance curve in the viral load. Josh will show you next week when we do this that you can actually then do a fit and actually get parameters that replicate quite precisely the experimentally observed viral load curves. And so it'll show that the model is sufficient to explain what you see. It doesn't mean it's necessary that it's correct. There are many models that could equally well explain those viral load curves. But it also means that it's not totally wrong, in the sense that if it were totally wrong, it wouldn't be able to do that. So I apologize for running out of time on this again, but I hope that talking about the conversion between methodologies was useful to you. Again, since I really want you to focus on doing the projects, I wanted to make sure that you had the tools to be able to build those project models. And if people want to go back and rebuild that preliminary model that you showed last week, using the things we discussed today to see if you can get them working better, that would be great. I know a bunch of people have just emailed me today asking if they can meet with me and or Josh, and we'll be happy to do that in the next couple of days. I don't promise you I will get the emails responded to tonight, but first thing tomorrow, I'll go through people's emails and try to set up meeting times. Are there any questions before we break for today? No. So the homework assignment will be 3 models of viral replication pulled from the literature. The first 2 will be taking ODE models and turning them into antimony. The third one will be taking a diagram, a arrow diagram, and turning it into antimony and running it. And the follow-up for those first two will be to turn them into antimony and run them. But for this week, we're not going to ask you to do that. It'll only be the first step of actually writing down the antimony. And so the key part of this homework will be to try to give people practice in going back and forth between what you see in a journal article and what you have to do to actually implement it. Any other questions, comments? People have been very quiet today. People tired? I'm tired. I don't know about you. Callie?
I was just gonna say, I didn't have any questions about the lecture content, but last week we gave the presentations in classes about our mini project updates, and I didn't realize we were supposed to also like submit our update to Canvas. So should I just send like whatever update that I have now to that?
Sure, that would be very helpful.
Okay.
I'd want to give you your points for it and at least look it over. And grading things electronically, I'm used to writing lots of comments on paper. And using the fast grading system in Canvas is not really a very good way to make comments. But I at least try to make a few comments. And if you have specific questions or comments, we can definitely meet and go over things to try to help make things work better. So yeah, if you can upload that, that would be great.
All right, thank you.
Okay, thank you. Anybody else? And I do need to get through everybody else in the class's presentations next week. So I do, and I hope people are able to make some progress. Okay, well, thank you, everybody. I appreciate you showing up. And I hope working through those exercises, I know it can seem a little tedious, but doing it together, I think, is important because these are skills that we're going to need and use again and again. Now that we have them under our belt, I think we can go a little bit faster. Okay, thank you, everybody. I'll see you one-on-one when we have our meetings and then as a group next week.
Thank you.
Okay, thank you. Good night.
Thank you.